Hello, my name is Akila, and today our group will present a design project entitled Semi-Automation Post-Processing System for Borneo Apong Golden Syrup. We have 5 member teams, and this is our member. The ultimate goal of processing the syrup is to eradicate the risk of microbes, in particular E. coli and coliform, to make it safe to eat. However, without very precisely controlled preservation and packaging measure, these products are highly susceptible to contamination. The challenge is to stabilize the syrup through thermal intervention without negatively impacting its sensory attribution, such as the natural sweetness level of the syrup. Apart from the temperature issue, we are also faced with mechanical integrity problem. The machine must be able to withstand high-speed operation loads without structural failure. At the same time, any weakness in the sealing quality of the sachet will be lead to leakage, which is then invite recontamination after the thermal process. Therefore, the design of our semi-automated post-processing system are developed specifically to solve these two critical issues. The goal of our project is to increase the commercial and economic value of local agriculture product through precise engineering solution. We integrate the preservation technology with the stick pack liquid packaging machine, which is capable of operate at a speed of 20 to 50 sachet per batch. Our focus is just on building packaging machinery, but designing a holistic ecosystem to ensure that these local syrup are free from microbial traits such as E. coli while maintaining their originally quality taste. For problem statement, first, the difficulty of achieving an accurate thermal control profile. If the heating process fails to be controlled, it's not only fail to kill pathogen, but also damage the sensory profile or sweetness of the syrup. Secondly, the challenge of maintaining the machinery integrity of the package and the stability of the machine structure. When the machine process are at high volume, its main components are exposed to static and variable loads that risk causing fatigue in the shaft and bearing of the machine. In addition, if the sealing jaw mechanism fails to operate at the optimal temperature and pressure on the third layer film, leakage will occur, further opening up the risk of free contamination. To overcome this problem, our design is driven by a structured approach. From the mechanical aspect, we have performed a failure prevention analysis by constructing a detailed free body diagram of the static and dynamic load, along with a strong calculation of safety factor. We also emphasize the selection of suitable structural material that are able to withstand the acidic property of the syrup to prevent corrosion. In terms of process, our machine is designed to ensure that sachets with a capacity of 10 ml are optimally sealed. The effectiveness of our machine thermal intervention is not randomly tested, but will be physically verified using data logger that is inserted into the product center to accurately record temperature versus time graph.
For our literature review, our apple syrup faces severe spoilage from microbial fermentation. Even though its high sugar content of 17 Celsius to 75 Celsius suppressed salmonella, its mild pH of 5.1 to 5.5 classify it as a low acid food vulnerable to forming microbes. Therefore, an integrated thermal pasteurization step is absolutely mandatory to guarantee food safety. From mechanical perspective, an enclosed processing system improves cleanness by 97% to completely isolate the syrup from acid beta contamination. For material, we utilize a rebut LDPE sachet limited to shield a hygroscopic syrup from tropical humidity, preventing surface moisture from reaching the safe 0.7 watt activity threshold. Finally, our Mechatronic framework integrates physical data logging to optimize the heat profile and enforce dripping cooling, completely avoiding nutrient loss and structural heat shock before automatic packaging.
You can see here is our post-processing machine designed by our group. It consists of an integrity tester for our sachet, a conveyor system, and a water tank. At left, we have the integrity tester, and at right, we have the water tank.
On the left side, we have the conveyor support. On the right side, we have the conveyor itself.
To analyze static loading, we decided to calculate minimum safety factor of L bracket, specifically at integrity tester's base. By measuring the support reactions, we managed to get a safety factor of 2.235, which is within acceptable range. We proceeded on finding minimum width for the L bracket by assuming the safety factor of 2, and we get the width about 4.73 millimeters.
For failure prevention from variable loading, so this is our free body diagram. And to find the factor of safety and first cycle leading factor of safety, we need to find the alternating stress. So by doing that, we will get 1.20 and 2.88. And then to find the minimum diameter of the shaft, we need to assume that the safety factor is 2, which will lead the answer to 39.93 millimeter.
For our first three designs, the water tank, conveyor shaft, and the frame, we selected hygienic 304 stainless steel and anodized 606335 aluminum to resist continuous H5 degree steam. For the manual basket, we use lightweight polypropylene to cut lifting weight by 88%, pairing it with die-cast aluminum L brackets to eliminate galvanic corrosion. Secondly, we map on our raw material costing using local kuching stockists in Demak, Laut, and SMI industrial parks, sourcing on steel, aluminum, and polymers locally at rates between 12 to 22 ringgit per kilogram, 5 passes expensive sea freight, securing a paycheck period under 3 years. Now we will talk about the power transmission and also the belting calculations. So to ensure controlled 300-second cooling time, our conveyor operates 0.0067 meters per second, creating a friction pull of 15.54 newtons, and also sized with a safety factor by 3.0. So our design powers of 0.312 watts is driven by a sealed directive drive 51 km motor, keeping the foot pad completely free of lubricant contamination. Ultimately, our system is fully validated with safe 1.44 mm volts and a direct drive 50 watt km running at 0.0667 meters per second to prevent syrup contamination. While statically safe, the conveyor shaft failed cyclic fatigue limits at 0.85, highlighting a critical point for future modification, and it's also cost locally in kuching. The system successfully modernizes regional food processing under SDG. Thank you so much.